Okay, welcome back to Calculus 2. Today we are going to talk about integration by parts. So if you remember, when we took the derivative of a u times a v, that was derivative of the first times the second plus the first times the derivative of the second. So when you have a song for this, there's other ways to do this. That's the way I remember it, and that's fine. Okay. And what I'm going to do is I'm going to say, well, we have the derivative of uv minus, this is equals, v du. Okay, and that is equal. All I did was subtract this term from both sides, and this is equal to u dv. And now what I want to do is I want to integrate both sides. Okay, so we're going to say that the integral of this derivative is going to be uv minus the integral of v du, and that is equal to the integral of u dv. All right, this is the formula for integration by parts. You have to pick a u and you have to pick a dv out of your function in order to put this thing together. Now, I don't memorize this formula. I do it a different way. Okay. I make a little box. So with doing this problem, okay, the first thing we have to do is like we have to integrate natural log of x. Like, well, I know the integral of natural log. It's 1 over x. Like that's not true. The integral of 1 over x is natural log of x. If you want to integrate that again, we don't have a formula for this. Okay, so if you remember, like integral of 1 over x dx, this is equal to natural log of the absolute value of x plus c. And if I want to integrate this thing again, then, well, shoot, I don't have an integral for this guy right here. We don't have, that's not one of the ones that we had to memorize. Okay, we don't know this one. So we have to do something else. It's going to be integration by parts. So what we have to do is we have to set a u equals, and we have to set a dv equals. Now, when I'm setting this up, okay, all of the pieces have to be accounted for. Like with u substitution, you can take your little calculus hammer and you can kind of club the functions into submission and do it the way you need to do it. But with these, you can still do a little bit of that, but mostly you have to kind of match these things up pretty well. Okay. Do I know the derivative of dx? Like, well, the second derivative of x, that doesn't really help. Do I know the derivative of natural log? Like, oh yeah, it's 1 over x. So we're going to say let u equal natural log of x, and then we're going to take that derivative. And it's like, that's 1 over x. So the piece that you're picking for your u is either the piece that is eventually going to go away, like if it's a polynomial, you have some power of x, it'll be like x to the n will be n x n minus 1. If you do this as many times as you need to do it, eventually that's going to be a 0, right? And then it goes away eventually. So if you have like an x squared, take the derivative as 2x, take the derivative as 2, take the derivative, oh, it's 0. That's the whole point. With dv, that's going to be everything that's left. That's going to be your dx. And v is going to be x. Go ahead and put a little d in here for that piece here. Now, in order to do my integration by parts, is we're going to do a cross and then backwards. Okay, it's a kind of like a flick and swish kind of a motion that we're going to be dealing with here. So the value that we're going to get here is uv, so that's going to be x ln of x, right, minus the integral of v du. Okay, so that's going to be x times 1 over x dx. Well, that's kind of nice because we have x ln of x minus the x's cancel integral of dx. That's an easy integral. I like that integral. That's going to be x ln of x minus x, and then we integrate it a couple of times actually, plus our c because it's an indefinite integral. And that's going to be my answer for this integration by parts problem. Okay. Now, if we want to go ahead and calculate what that's going to be when we take the derivative, because remember, if we take this derivative, we should get natural log of x when we're done, right? So if I want to take this derivative, then I have to remember this. It's like, okay, we're going to take the derivative of x ln of x minus x plus c. Okay, so as I'm taking the derivative, remember it's derivative of the first times the second plus the first times the derivative of the second. Okay, minus, I'm going to go ahead and take the derivative of this piece right here. And we're going to go ahead and take the derivative of that piece right there, right? Because derivatives will go through linearly and we'll just be able to kind of apply the derivative to each of these different terms. It's just that when we had a product, we had to use the product rule, okay? So derivative of x is just going to be 1 times natural log of x plus, here we have x times the derivative of natural log of x. That's going to be 1 over x minus derivative of x again is going to be 1. And the derivative of a constant, of course, is 0. So we end up with natural log of x plus x is canceled. So we have an 1 here minus a 1 plus 0. And we actually end up with natural log of x. So we took its derivative, we got the natural log. We took the integral, we got x ln of x minus x plus c. And that is our answer for the integral of natural log x. Okay, so there's a couple of times and places where you're really going to want to be able to do integration by parts. Anytime you have a natural log in there, it's usually an integration by parts problem. Not always, but often. When you have a polynomial times a trigonometric function, it's going to be integration by parts. All right. So with this one, we have to go ahead and pick out the ones we want to pick out. So we're going to say let u equals, well, I've got a choice. I could pick an x, I could pick a sine of 5x minus 1, and I've got to attach my dx in there somewhere. Which one of these is eventually going to go away? You take the derivative of sine, we get cosine. We take the derivative of cosine, we get negative sine. It kind of flip-flops on and on and on and on and on. Take the derivative of polynomials, and we end up with smaller functions. So I'm going to pick u to be my x. du, of course, is 1. dv, right, is going to be sine of 5x minus 1. Okay, and then we have to integrate this. So integrating this guy right here, I'm going to go ahead and do my little notes page that I have here. If I have a chance to mess this up, I will. So we're going to end up with negative 1 over 5 cosine of 5x minus 1. Let me just go ahead and take the derivative of this cosine 5x minus 1 real quick, and we're going to get a negative sine 5x minus 1 times its d times its chain function times 5. So that's why this 5 over here cancels. So here's what we're going to do is we're going to take our uv minus our vdu, integral vdu. So we're going to say this is going to be x over 5, we'll put the negative here, times cosine 5x minus 1 minus the integral of negative 1/5 cosine 5x minus 1, we'll put a dx in here, times dx. All right, so that's what we have for this piece. All right, some stuff is going to cancel. So we have negative x over 5 cosine 5x minus 1 minus plus minus minus. So we have a plus integral of 1/5. Let me go ahead and move that out of the way. Okay. So we have a 1/5 sitting here. We had a negative times a negative. It's a positive. Cosine 5x minus 1 dx. And we have to go ahead and integrate this piece. Okay. So I know the derivative of sine is cosine. So the integral of cosine must be sine. So here we have negative x over 5 cosine 5x minus 1 plus. Here we're going to say we have 1 over 5. I have to integrate cosine of 5x minus 1. That's going to be 1/5 sine 5x minus 1. Okay, and there's no more dx here. So let's go ahead and clean this up a little bit. So we have negative x over 5 cosine 5x minus 1 plus 1 over 25 sine of 5x minus 1. And now that I'm pretty much done with this idea, we're going to add in our plus c, because we can't forget that. Okay, but that's going to be my answer to this integral. All right, we don't have to check it. You have to check every time. That's okay. Right, we know that we're going to be okay with this, but that's going to be our answer for this integral here. All right, and that's how you do this. So when you have a polynomial times a trigonometric function, it is screaming at you, do an integration by parts. Okay. Another one that screams at you is when you have a polynomial times an exponential. Might be noticing a trend here. Okay, so we have a polynomial times an exponential. It's telling you it's integration by parts. When you have a polynomial times trig, it's integration by parts. When you have a polynomial times a logarithm, it's integration by parts. Pretty much, remember how we started this? Is we said, oh, what do we do when we take the derivative of two functions multiplied by each other? So when you have two functions multiplied by each other in an integral, that's pretty much kind of telling us like, hey, there's an integration by parts going on here. Not always, but mostly. Okay. So we're going to be able to say this is u is equal to x, du is equal to dx, dv is equal to e to the negative 4x. We're integrating this, remember? So that's negative 1 over 4 e to the negative 4x. Now, what I do is I quickly go through and kind of take this derivative again by just by inspection, right, in my head. And it's like, do I actually get the same thing that I started with? So if I took this derivative, we're going to get negative 1/4 e to the negative 4x times 4, negative 4. The negative 1/4 and 4 is going to cancel, and we actually end up with e to the negative 4, e to the negative 4x. So I'm okay with what's going on here. So we're going to do flick and swish here to go ahead and get our integration by parts here. So we have this is going to be negative x over 4 e to the negative 4x minus the integral negative 1/4 e to the negative 4x dx. Okay, some stuff clears out. So we have negative x over 4 e to the negative 4x plus the integral of, we'll put the 1/4 out here because we can slide that through the integral sign, negative 1/4 x dx sitting here. Let's go ahead and integrate this. So we have negative x over 4 e to the negative 4x minus, because we're going to end up with a negative, 1/4 times another 1/4, so minus 1 over 16 e to the negative 4x. Actually, let's do that a little bit slower so I don't do the whole thing really that fast. Okay, so let's go ahead and do this. So I've got a 1/4. Okay, I've got a plus 1/4. Now we're just integrating this little piece in here. That's going to be 1 over negative 4 e to the negative 4x. I could swear I've seen that before, sitting right up here. Okay, so just to kind of double check, did I do this right? Like, yeah, I did this right. So we can go ahead and let's start combining some things. We have negative x over 4 e to the negative 4x minus 1 over 16 e to the negative 4x plus c. Don't forget your plus c's. All right. And that's how you would do a problem like that. Right. So that's how that one works. All right. Let's see here. We have one more to work with, and this one's going to be a little bit harder. I think this is a nice little introduction to integration by parts for you. Okay, the next time is integrating inverse trig functions. Okay, we had to take derivatives of all the inverse trig functions in Calculus 1. If you've forgotten how to do that, go back and remember all those rules for what those things are because you're going to need them again. This one is a definite integral. We'll see how that fares. Okay, so almost always when you're trying to work this thing out, there is a little, if you look on the internet for people to do integration by parts, and you will find dozens upon dozens of videos for doing this. You will come across the DI form, which is in your book, which is great. I don't usually teach it because when I teach this, I usually teach elements of calculus students, and they don't always know when is the good time to use this and when isn't. Okay. You're going to have to know like when is the good time to use this and when isn't. Generally, when you're working with things that are going to eventually turn to zero, that's a good time to use this. All right. But without that, like I would suggest not using the shortcut until you're sure. But generally, the way that you're going to pick what should your U be is for a logarithm, that's your first choice, an inverse trig function, an algebraic function, a trig function, and an exponential. Okay. This is algebra. This is inverse trig. Okay, and then a log. So this is generally like your choices for your use. Now, this doesn't always work. Okay, there's times when this will not work for you. It frequently will, but don't be afraid to think this is a guideline, not a rule. Those are different. Okay. So if you want to remember this is a guideline, that's probably a good thing to do, be able to do because most of the time this will work for you. But understand most of the time ain't all the time. So like, oh, that didn't work. I wonder where I went wrong. Go back to what you picked for your U, maybe pick something else. Okay. So for this one, um, you're pretty much you have to pretty much use, because I can't take the integral of secant inverse. I don't know what that is. So when I'm picking this out, we have to say let u equals secant inverse of x, okay? And then going back and remembering how that works, that is 1 over the absolute value of x times the square root of x squared minus 1. This is one of those formulas you had to remember. Um, I'm going to go off on a thing here and say, since my x is between 1 and 2, x is going to be positive. So we can go ahead and get rid of that absolute value because it's always going to be positive. This is just going to be 1 over x times the square root of x squared minus 1. All right. My dv in this case has to be my x dx. It's whatever's left, right? I already used up my secant inverse. The things that are left was my x and my dx. So my v is going to be 1 half x squared. We'll put the c in at the end, okay? So pulling this together, we have our u times v. That's our flick. And then we have our swish. And we're going to be able to figure out the rest of this piece here. So let's go ahead and put this out. So we have 1 half x squared secant inverse of x minus the integral of 1 half. Here we have an x squared over x square root x squared minus 1 dx. All right. And that's where we are with this. Well, fortunately, this kind of simplifies down a little bit. So we can go ahead and get rid of some of this stuff. So we have a 1 half x squared secant inverse of x minus 1 half integral of x over the square root of x squared minus 1 dx. I'm going to go ahead. Usually I like to let different letters, I've already used up u and v in this problem, but since u is so common, we're going to go ahead and do this real quick a little bit here. So we're going to go off to the side and say let u is equal to x squared minus 1, du equals to 2x. Okay, so we're just integrating this little piece in here. So what I need is a 2x in here, but I can't go around multiplying by 2x. So I multiply by 2x here, but I divide by 2 out here, okay, in order to keep this straight. So this piece here is now my du, okay? And this piece under here is going to be u to the negative 1 half power. So let's go ahead and do this. So we have 1 half x squared, okay? Secant inverse of x minus 1/4, right? And then we have our integral of u, and then we have I'm sorry, that's not a u there, that's a du sitting up there, okay? We're going to go ahead and do this. So we're going to say this is our du here, and we're going to have since our u is equal to x squared minus 1, this is u to the negative 1 half power. So we'll go ahead and integrate this piece here just using power rule. So we have 1 half x squared secant inverse of x minus 1/4. We're going to go ahead and say this is going to be u to the 1 half, but I had to multiply by 2 over 1 in order to make this thing work. So last things here, we have 1 half x squared secant inverse of x minus, we have 2 over 4, that's 1 half. And then what was my u? My u was x squared minus 1, right? But it's in the numerator now, so that's fine. And is it plus c? No, no. We're going from 1 to 2 here. Okay, so we have to go ahead and plug these things in order to get a numeric answer. So we've got 1 half times 2 squared secant inverse of 2 minus 1 half of 2 squared is going to be 4 minus 1 to the 1 half power. All right, and that is x evaluated at 2 minus. Now we need x evaluated at 1. So this is going to be 1 half times 1 squared. So it's going to be 1 half here. Secant inverse of 1 minus 1 half. And then we have the square root of 1 minus 1. Okay, and we'll have to figure out what's going on here. So let's go ahead and do this. Square root of 1 minus 1, that's going to be, this is x evaluated at 1. So we can go ahead and figure that out. So this piece here is going to be 0. That's nice. And this piece here is going to be 3. That's great. So let's go ahead. Let's figure out what the inverse secant of 2 is, and figure out what the inverse secant of 1 is going to be. So we have 2 squared, which is going to be 4. 4 divided by 2 is 2. So we have 2 secant inverse of 2 minus the square root of 3 over 2. That looks like it came out of a trig problem, doesn't it? Minus 1/2 secant inverse of 1, and then we have a minus 0 here. We're going to leave that alone. Okay, so now the question is, what is the secant inverse of 2? So secant inverse of 2 is equal to some kind of a theta. Okay, I don't know what it's going to be, but it's going to be some kind of a theta sitting here. Okay, or some kind of a value. Okay, and then we have secant inverse of 1. Well, what's secant? It's 1 over cosine, right? So this is really cosine inverse of 1 over 2. Cosine inverse of 1 over 1. Okay. Okay, so what is the inverse cosine of 1? Well, cosine of 0 is 1, so this is equal to 0, right? That's the angle 0. And then we have inverse cosine of 1/2. I don't know what the heck that is. It's not a nice number, but at least we're sitting here with this. Okay. Actually, I think we could say something about this because I think cosine of 1/2 here is pi over 6, pi over 6, pi over 4, pi over 3. I think that's pi over 3 sitting here. Okay, so we can go ahead and do that. So we've got 2 times pi over 3 minus square root of 3 over 2. So let's see, that's 2 pi over 3 minus square root of 3 over 2 minus 0. So this is going to be my exact answer. Okay, let's go ahead and see what happens with this. So we'll go ahead and we'll plug this guy in. So we've got 2 times, where's my pi for this guy here? Right there. 2 times pi divided by 3. Okay, equals minus, we'll do the square root of 3 and my parentheses divided by 2. And we'll say equals, and I got 1.2283, so set it 1.22, let's see what we have here, 1.22837. Okay, so this would be my exact answer. Okay, sometimes they'll tell us like, hey, put this to 4 decimal places, and we'll just kind of truncate it right there and let that go at that piece right there. So that's how you do an integration by parts problem. Okay, we did both indefinite and definite integrals for those things. Things you want to remember is you want to remember the DI thing. I'll show you a problem like that a little bit later. I'm not a big fan of this, but I know a lot of students really like it. And if you go looking on YouTube, you're going to see a lot of people who really like the DI system. Okay, and that's fine. You're allowed to use it. It's just realize like when you are allowed to use it, when you're not. Okay. And then we also talked about LAITE. Again, what do you pick for your U? This is, again, this is not a rule. This is a guideline. Just be really careful with, like, it's a guideline. It's not always going to work. So just be aware that, like, hey, this didn't work out very well at all. Like, yeah, it didn't. And that's too bad. So you can't use it. Or you have to use it for something different. So be careful about using this. Okay. So I think that's all the problems I wanted to show us in this video. So I'll say thank you very much for watching. I will see you on the next one, and take care.